Hello everyone, my name is Escorza and I want to contribute to the discussion about the unsolved problems in evolved stars by talking about barren stars. The specific problem I want to address today is the determination of stellar masses. Stellar masses are a key parameter in astronomy. However, they are very difficult to determine. Stellar masses have a very strong impact in phenomena that we need to understand if we want to study stars. For example, the stellar evolution, the final fate of stars, their internal structure, the chemical production in their interior throughout their life, and many other aspects that I'm probably forgetting. However, unless you are very lucky and your favorite star is in an eclipsing binary system or is a very specific type of pulsator, you are probably going to struggle to determine its mass accurately and precisely. Additionally, if your favorite star is evolved, you will also have to deal with large radii, messy convective atmospheres, mass loss pulsations, and other phenomena that make this task even more difficult. So I'm going to focus here on AGB stars, but in order to learn about AGB stars and the AGB phase, I want to look at the progeny of these systems. More specifically, barium stars, as I said before. Barium stars are the progeny of AGB binaries, post-interaction products. And I have listed here other post-interaction or post-AGB binaries that we could use as well. Barium stars form in a system like this one that I'm showing you here. Time goes from top to bottom, and we have a binary system with two stars, one of them more massive than the other one, and this one evolves faster. This star reaches the AGB phase, while the secondary is still unevolved, and produces in its interior carbon as process elements and other typical products of AGB nucleosynthesis. In an episode of binary interaction, it pollutes its secondary, and time passes, and we are observing the system's time after, when the secondary star, the polluted star, is the primary star of the system, and the former AGB star is a cool white dwarf that we cannot directly see. The exact formation scenario, numbers, periods, mass ratios are not well known, but what we want to do is to look at these systems, the barium star plus white dwarf, understand them as well as we can in order to take a step back and learn about the AGB phase. We have done some progress in this aspect. We have determined barium star masses, and we have done these as accurately and precisely as we could using high-resolution spectroscopy, distances, state-of-the-art evolutionary models. And here you have the HR diagram on the left of a sample of dwarf and giant barium stars, and the mass distributions that we determine for these objects on the right. Additionally, in order to learn about the white dwarfs, which are basically undetectable, as I mentioned, but they are the ones that contain the information about the AGB star. We also need to learn about their orbits, the binary systems. We also did this, and here I show you the eccentricity and the period of the same sample I showed you before. And a product of orbital fitting is the mass function. The mass function is this relation that you see over here that relates your orbital parameters with the masses of the two stars of the system. We have M1 from the previous slide, and we want M2. However, we still don't know the inclination, and it's difficult to determine inclinations for single-line spectroscopic binaries. That's why we are now invoking astrometry. What we are doing at the minute is combining the orbital information that we have, that I just showed you, with Gaia and Hipparcos astrometry in order to get information about the inclinations and information then about the white dwarf. I show you here a table with a few objects for which we already did this, and you can see that the companion masses that we determine are meaningful and also quite accurate. Why is this important? Why are these white dwarf masses interesting for the community? Well, if we combine them with the knowledge that we have about the chemistry on the barium star, we can learn about the efficiency of the S process at different masses and metallicities. And we can also, for example, produce an initial final mass function for this type of objects, or we can determine the mass ratio that we need in order to form a barium star, which, as I said, together with the periods, the eccentricities, are not known parameters. I'm sure you can come up with other questions that these white dwarf masses can help us address. And with this, I hope, thank you for your attention. I leave here my contact information and some reading homework. And I also ask you to stay tuned because we are working on these wide masses and we'll publish them soon. Thank you very much.